That's where it was.
All right, I think we'll get started.
It's on. I heard you do it.
Can I just take down?
Are you able to disseminate slides? Is you able to disseminate the slides?
Yeah.
That sounds good.
All right, so welcome everyone. Thank you so much for taking the time after work to come and join us and talk about different sampling techniques for handling imbalanced data. So kind of give you guys a little bit of background into why I wanted to do this talk. I mean, I think part of it was definitely that, you know, it's very accessible to us to import packages and know that they work, but do we really understand what's going on? And so specifically, I wanted to focus on a particular technique called SMOTE. Before I do that, I kind of like to get a general sense of the audience. So do any of you guys work currently as data scientists? No, data analysts? Software engineers? Okay, cool. Marketing? Yeah. Anyone else? And then students? Students. Awesome. Engineers. So this is great. I think there are a few people that used to come to my old meetups are here, so thank you guys for making the drive out. For those of you guys who are new to my meetups, just a little bit of brief background. So I started doing this about, I want to say like a year and a half ago, when I first started learning machine learning. So I have a background in math, economics, and statistics, but machine learning was kind of a new area that I realized my company was moving towards, and so I had to learn as quickly as possible, and so my way of learning is teaching. So, so I started these meetups. I tried to be as consistent with it as possible, so once a month was a good cadence, and I just choose a topic that I liked, and so hopefully you guys will find this interesting, and you know, nuggets that you guys can take away, kind of take you guys through my journey of how I'm learning this stuff. So in case you guys can get the internet, it's right there, and okay, another brief introduction of myself. I work as a marketing analyst here at Mobilityware. I've been here for 2 months. And if you want to follow me on LinkedIn, that's my link. And then my co-host, Eric Weber, who's helping me put together the slides and kind of just helping me overall. He's a principal data management at ROC.
Not really. Awkward introduction, but all right. So I'm Eric, and I'm happy to be here tonight. I think over the coming months, I'll be doing some of the presenting as well, sort of be trading off back and forth, unless Sarah just decides she wants to just take it all. I'm good. I'm good at eating pizza. I'm just kind of sitting over here on the side. So my background is somewhat similar: math, statistics, data science. I was in academia teaching for about 5 years. After that, I was in the Bay Area at LinkedIn, and I've been down here on half now, somewhere around there. So I am running a large part of our data science team and data management team at CoreLogic. So we're in Irvine. Mobility gets precedence for advertising their open job openings because, well, look where we are right now. But we're also building out a team. We focus primarily on property, criminal, and financial data. So if you look up anything, you're looking for houses, stuff like that, our data kind of sits behind. Looking forward to meeting you guys.
Okay, so that's us, and a big shout out to MobilityWare. So yeah, like Eric was saying, we are hiring. If this picture doesn't tell you a lot about the culture here, it's pretty awesome. I've worked in a few places, even, this has kind of been a great place where I get to call some of you guys my family, and I appreciate that. So definitely, if you find anything, definitely mention my name, so I get a referral bonus, right? Okay, so moving on. So kind of a general outline of how I plan to structure today's talk. So the first thing we want to do is kind of define balance. We're going to start from the very beginning. So it sounds like the majority of us are not actually working in data science, so kind of taking it one step at a time and building up the knowledge at the end would be a good idea. So we'll do that. Then, now that we know what it means to be in balance, why is that an issue? So we'll talk about where that becomes a problem, and then some possible remedies for it. And then, has anyone heard of SMOTE? So we all have something to learn today. That's exciting. And then I'll go through a brief demo. Does anyone here know what I'm talking about? Okay, so some people are familiar with that. Great. So some of it might be new, some of it might get to see it in action. So first thing we want to do here is define balance. So here's a nice quote, but maybe it'll just be a bunch of jargon, we'll see. A data set is said to be balanced when binomial or multinomial response variable has one or more classes that are underrepresented in the training data with respect to the rest of the classes. So when we read this, we generally understand what it's saying. How many people kind of understand? Okay. So here, when we're talking about a binomial or a multinomial response variable, we're talking about what types of problems? Classification problems, correct? So we're dealing with a classification problem, and in the simplest case, where you have a binomial response variable. So we'll kind of focus on that, and you can kind of generalize out to multinomial cases. And then do we understand what it means to have training data? What is training data used for?
Training data is used to build your algorithm with a small section of your data set. It's reserved for running iterations of your algorithm as you build it. And once you get to where you want to test it, you use the test. That's a separate set of testing data, but you never touch the outlying data. You don't want to bias it.
Is it algorithm or model?
The training set. So the training set is a part of your entire data set that is used to essentially build the model. And then it's evaluated on our testing set. So it's important to distinguish between the two because what we're going to do in our possible remedies is look at what we can do to the training data up to build the algorithm, but we don't touch the testing set once we build our model. So we're looking at that training set, and there's a huge class of balance that's going on. So what does that kind of look like? Kind of looks like this, right? So we have two classes, and in the best case, you have something that looks like this, right? 50-50 split down the middle, where the negatives are approximately equal to positives, but something like 40-60 split could also be fine and not really affect our model that much. Where we start to run into problems is where we have majority of our class being taken over by negatives in the class. So by convention, we refer to the minority class as the positives and the majority class as the negative class. So this is not the most extreme case that you'll find. typically you'll find 10% or less than that, maybe like 1% showing up, and we'll look at cases like that. So what does that look like? This is another visual of kind of the data set that we find where we have approximately equal number of data points in either set. And this is kind of a more realistic version of what you would see when you're looking at a data set with high imbalance, where not only is the minority class smaller than the majority class, but it's also somewhat hidden, right, within our majority class. So it's very hard to tease out. Kind of here you can see if you could create a boundary, decision boundary between these two lines, so it would be very hard. So, real world examples. Does anyone know any real world examples?
There a couple of years ago, there was a casual competition on click data, and the click data fraud actually, where they had bots that were doing like 5,000 clicks in like a second.
Okay. Yep. So click through data or click data. Anyone else?
The percentage of people in our markets that
Yep. So payer percentage. Yes. Yes.
presence of certain diseases.
Yep. So cancer, medical screenings. So yes, these are all great examples of where we will find high imbalance. So fraud detection wasn't mentioned, but this is fraud detection. Okay. Shows up maybe like less than 1% in a particular data set. I'll actually test the one that Kaggle put up that has less, I think it was 0.17% of the classes fraud of the data sets. It's actually fraud, and so we'll look at that data set as an example. I think it was mentioned, so medical screenings, click data, device infection, spam, cancer, right? So all of these are great examples where we'll be dealing with where we'll be dealing with highly imbalanced data. And notice how each of the outcomes here have different consequences, right? So in certain cases, maybe in this classification is much more costly than another case. So we'll look at metrics that will help us evaluate that. So why is imbalance an issue? So it's an issue when we're building our models, and especially at the point of evaluation. So when we're looking at a model, how do we normally look at and whether it's performing well or not?
Yes.
Yeah. So do you have a name for that? Anyone? Not overfitting? Solution. Okay, so how do we normally evaluate our models after we've trained it and now we're looking at its work? Yes. Anyone? Great, so that should be the way that we do it. How do we normally, what's our first line of defense? Our accuracy. Good job. So we look at accuracy, right? We want to see how well did our predictions match up with the actual data set. So in this case, where we do have a high class of balance, actually accuracy falls apart, right? Which is why you guys are telling me all to look at that. So because conventional algorithms are biased towards the authority class, it'll attempt to optimize towards accuracy, and in that case, actually give us a very not good classifier. So in the extreme case, let's say you have two classes, right? And it's kind of mimicking the diagram we had a few slides back, where we saw that 90% of the data set was the negative class, right? And then only 10% positive. So if we were looking at accuracy here, we were looking to optimize that, then the classifier would basically say, okay, well, I'm going to predict everything as a majority class and get you a 90% accuracy. But that's not the type of model we want, right? Especially when what we care about is the proper classification of the minority class, right? So, are you agreeing on this? TPR, FPR, precision, and recall. Okay, so let's move slowly. TPR stands for the true positive rate, correct? So, and FPR stands for the false positive rate. And we have precision and we have recall. So, essentially, some of you may like this illustration, you may not. That's fine. So, okay. So I like this diagram because I think it does a good job of. So, okay. So when we start looking at this diagram, essentially, a sample that you predict can fall into one of these four categories, right? So it could be a true positive, meaning it's actually positive and we predicted it to be positive. It could be a false negative, means it was actually positive and we predicted it to be negative. A false positive, where it was actually negative and you predicted it positive. And then true negative, means it was actually negative and you predicted it. So the reason why I like this diagram is because if you follow the black line, then to the left of it is all your positive predictions. To the right of it is all your negative predictions. And then if you split by the white gap, then the top is basically all your actual positives, and the bottom is all your actual negatives. So it's really easy to distinguish what part of this diagram you're looking at, especially when you start looking at metrics, right? So when formulas pop up. So the true positive rate actually takes on another name, depending on what industry you're working in. Sensitivity and specificity, where in the kind of data science realm use true positive rate and false positive rate. So the true positive rate is going to look at basically the top half of this diagram, right? So it's of those that are actually positive, how well did we do at positive? And then the false positive rate is looking at the bottom half. It's of those that were actually negative, how many did we misclassify as positive, right? Okay, so these are two important metrics that we want to look at, as well as recall and precision. So what do we immediately notice when we pull up recall and precision? Yeah. So recall is exactly the same definition as TPR. So these three things are the same. True positive rate, sensitivity, and recall are all the same thing. And then we have precision. So precision is looking at this part of the diagram. And it's basically saying, of those that we predicted positive, how many of them did we get? Right? So precision has this extra meaning to it where you'd rather not make a prediction than make a prediction and it be wrong. So and I don't know if I'm seeing power there. To say this now. So TPR and FPR have a nice quality to them in that they stay within their classes. And that'll become important in a second. Precision, however, do you notice how since it's going diagonally, it's kind of affected by the different classes. Any questions so far? Okay. Great, we made it through the first one. All right, now ROC and the precision recall curve. So while we were looking at these metrics, and we see that they're all telling us something about our misclassifications, right? So they're telling us, essentially by looking at these four metrics, we can decide, depending on the business problem we're trying to solve, which one we care about more, right? So, assuming, let's say, we're dealing with fraud detection, then if we had misclassified something not fraud as fraud, maybe that just adds more time to the people who are sifting through fraudulent transactions and find out that it's not, right? That's a fine misclassification to make. So maybe in that case, recall would be a great metric to use, because I don't care if the precision goes down. right? But if the cost of misclassification is actually even higher, maybe in the case of misdiagnosing cancer, maybe you would care a little bit more about how accurate your precision is, right? Okay. So now, when we're introducing those metrics, we have to realize that it's a trade-off, right? It's a trade-off between our true positive and our false positive rate, and it's a trade-off between precision and recall. So this is a classic way of kind of approaching the model selection and the model evaluation after we train. So what this is showing, it's called a receiver operator curve, and I don't know if you guys care to know the history behind this. Yes. Okay. So in World War II, there were actual people who would sit behind radars and look at the data. And they actually had these curves associated to each person depending on how good they were at classifying things as an actual threat or not a threat. So they were called receiver operator characteristic curves. So that was based off of that. So essentially, after we've built our model, we can look at something like this. Anything that lies below this curve is probably not doing a very good job because this line represents randomness. And anything above this curve is saying, okay, I'm doing better than randomness. So, and then between maybe the red and the blue curve, you would say the blue curve is doing better because it's optimizing kind of our true positive rate as we move on. If we wanted to tie this into one metric, let's say that we wanted to use to evaluate the different models, we can kind of consolidate that into an AUC, or the area under the curve, which is basically taking this ROC curve and just integrating to get the area underneath. And so that would give us our AUC. We can also use something called the F1 score, which is just the harmonic mean between precision and recall. And one thing that I do want to mention here is that since the AUC curve is based off of TPR and FPR, and these are not influenced by the different classes, they don't dip into the different classes, this is probably a better metric to use for evaluating than the F1 score, because the F1 score uses precision, and precision is looking at both classes. And here is kind of a diagram to illustrate that. So here we have kind of a model that was built with, these are the ROC curves for a 1-to-1. So they were a balanced data set, and these are the ROC curves that came out of that. And then these were the precision recall graphs. Now, when there was a high skew, right, now 1 to 10 imbalance, we see that the ROC curves are pretty stable, and the precision recall graphs have clearly been affected. Great, so possible remedies. Who knows some possible remedies?
Consider the lower data set.
Okay, yes, so minority oversampling, right? Anything else that we can think of?
Majority undersampling, that doesn't.
Undersampling, okay. All right, so those are two very common methods, right? So here's some possible remedies. Let's say the first case is that you get very lucky, you have very good descriptive features, and so you don't have to do anything, right? That's the lucky case. Another case here is that you're actually going to try and balance the data, the training set using a few sampling techniques. Some that we just mentioned, right? So we have oversampling, undersampling, there's different types, or a combination of the two, of oversampling and undersampling. We can also do some cost-sensitive learning, maybe a move to an anomaly detection, or in the worst case or very expensive case, that you buy or create more data, right? Depending on the business case, this could be actually very, very expensive. So one that we are going to talk about today is synthesizing new examples using SMOTE. So SMOTE stands for Synthetic Minority Oversampling Technique. Okay, great. So what does it look like to oversample or undersample? So if we look at the top half, this is our entire data set, right? This is our majority class, this is our minority class. So in order for us to kind of create a balanced data set, we'll continually sample out of with replacement. I don't know if those words sound foreign. We'll sample with replacement from the minority set over and over and over again until we have enough points that they're kind of equal, right? So now this will be our balanced data set that we can train on. The alternative is undersampling. So here is our minority class, here is our majority class, and we randomly pick samples out of the majority class to create, again, a balanced data set, right? So here is another visual, and notice how when we do undersampling, we lose a lot of data, and when we do oversampling, we end up with a lot of data. And it's not necessarily clear which one is better. Doing this doesn't always resort to a better, oversampling just because you have more data doesn't always result in a better model. So sometimes a combination of the two. Another way to attack this is by using class weight. So if you know that the cost of a misclassification is 10 times that of the cost of a false negative, false positive? False negative is 10 times more than that of a false positive, then maybe you could just adjust that into your class weights and have a more conservative decision boundary as a result. Right? So that's a possible remedy. And then the one that we're going to talk about today in a little bit more detail is synthetic minority oversampling technique. Are we all excited? The smoke. So something that I see that's very common in the data science community is that because there is so much to learn, because it's so broad, it's hard to know everything in extreme detail, right? So we know things on the surface, and because it's so easy to just import the package and use it and see that it works, we don't actually care to know what's happening under the hood. So today, hopefully, we'll get to learn a little bit more about what's happening under the hood of SMOTE. So a little bit of kind of what's been happening to date. We know that undersampling the majority class enables better classifiers to be built than oversampling. That's kind of what they've researched so far. And then a combination of the two leads to classifiers that outperform those by using only undersampling. So combinations of the two, does not lead to classifiers that outperform those utilized by just undersampling. But the caveat here is that the oversampling of the minority class was done by just picking the same ones over and over and over again, right? So this causes a problem. So what SMOTE is going to do is kind of create new sample points based on the existing ones in order to kind of help with generalization. So it's a different type of oversampling. So the disadvantages of the prior methods is that right here. So it didn't generalize very well. So what's happening here? It looks like this was the decision boundary that happened when we did nothing. And then when we oversampled the minority class by randomly picking over and over again, these are the decision boundaries. I don't know if you can see them clearly. They are tiny. And specified on one point, right? So it's not very generalizable. It's basically producing these very specific decision boundaries that are just very hyper-focused on a few points. And I'll show you guys, it's not very clear here, but it's probably, this is a very dark point because it's been sampled so many times, right? So this is, we propose, not me, these people. So these people who wrote this great paper, if you're interested, you should read this. It's not too hard. So they basically talk about their approach, kind of the literature to date, and kind of the approach that they took to create these synthetic examples rather than sampling over with replacement. So the motivation for this technique was based off of the handwritten character recognition, right? It's kind of the classic machine learning image classification. And essentially what they did to create more data, right? Because that's kind of an issue that we run into is, okay, so with images, what they did is they like rotated it, transposed it, turned it around, and all of a sudden you have many more training examples that are still classified as what we need them to be. So that's kind of where the motivation for this comes from. So the minority class is oversampled by taking each minority class and introducing synthetic examples along the line segments joining the k nearest neighbors. So what it's doing is if we're looking at x1, then it's looking at its 5 nearest neighbors, which is the default. So it'll look at the 5 nearest neighbors, and then depending on how much we want to oversample, let's say we want 100% more samples, then we would choose 1 nearest neighbor, and then it would generate across just 1. So to make this a little bit more concrete, so let's say we wanted to oversample by 200%. So then we would choose 2 neighbors from the 5, and then we randomly choose those 2, and then generate samples in each of those directions. Okay? Okay. So I did this. 5 nearest neighbors are these green ones. And then I've created essentially, I've randomly chosen 2, this one and this one. And I've generated these samples, new synthetic samples, in either direction. Easy enough? Alright. So how is it being done? So mathematically what it's doing is taking the difference between the feature vector and the nearest neighbor, and then it's basically taking a random number between 0 and 1 and then adding it to the original feature vector. Right? So, more concretely, this is what's happening. So we have an example, a sample 6,4, and then 4,3, let's say, is the nearest neighbor to it. Then we're taking the difference between the, let's say, the first feature, 6 and 4, and getting -2. And then the second feature, 4 and 3, to get -1. So this becomes what we add to the original sample, multiplied by a random number between 0 and 1. Good? Thumbs up? So, all right. So that's that. So now the advantages, right? Yeah.
What's the role of random?
Just to make sure, what? Right. The role of the random number.
It sounds like you're trying to contradict this.
You're not, yeah, trying to.
Honestly, prefer, yeah. Don't want to, you want it to generate a different set of points.
So in case that let's say in the case that it went here and it was limited to only maybe these 2 points every time, if it was to continue to generate the same point in the same spot, then it would just be doing the same thing as we did in the prior, right? It's creating so many points.
So if you have to oversample more than once or twice.
Exactly.
Yeah, and this is also an issue that if you are doing the sampling and you do it within a notebook, within R or Python, and you don't set the seed number, you won't be able to reproduce anything.
Oh,
Right? Because it's taking
It's
random numbers. So something to consider.
Okay. Any other questions?
Actually, do you ever take into account the other class when you're choosing that, or?
There are variations of SMOTE called like borderline 1, borderline 2 that do take that into account, but I'm not.
Worry about that feedback. And pick another one, as long as it's not one of the ones that look close to the other class members.
Yeah, that's
Start to buy itself.
that's a good point, and I think those 2 different variations take that into account. Yeah, so there's things you can do there. So the advantage here is that
I'm not a data scientist. I feel like something is those, it's like you're starting with assumptions you've already inserted, so all we do is values randomly. So I feel like it's a flaw in that. Because if you're looking at like multiple variables just because I can take the value of your interpolate, doesn't actually mean that that data is not training data is correct. We've made an assumption that it still falls just because it interpolates between these two. It must be accurate, so feel like this is just a flawed assumption, that's okay. But it's maybe simple if you're like, oh, how much money do they make? Well, what if it's like 3 or 4 different variables that come up together? And then, oh, I interpolate these two, interpolate these two. I'm sure that that's also an accurate. Yes.
Yeah, I mean, so what essentially we're trying to do is just generate more data so that the decision boundary can be a little bit more accurate. So, I see your point. Do you have a better answer than PDF?
I see your point too.
How data science, so maybe you guys are just okay with that.
No, so-
I'm missing, I'm missing. I want to do like a distribution on first to see if we're just talking about the problem. Which has like a smooth. You're just generating data.
Well, that would be okay with like smooth distribution for each feature, but if the features were like, not like, considered like binomial shape or something.
Yeah.
Like binomial distribution that really is saying.
Or if the other factors influence each other, so it may not be the case that this one just because it interpolates here. Actually, this variable plays with the other variable, so it matters both how much money and where they live, and whether they use a credit card before. It's not just how much money you have, so it just interpolates. And then usually these things will play together.
So they, these are supposed to be like, pieces you're talking about are two things.
Oh, is that true?
Yeah, so like, we're talking about the positive and negative, you have cancelled those are the outcomes. Trying to separate.
Yeah, the outcome, the final outcome.
The features that they gathered together, they should be combining. The other ways to handle features are related to each other, like, you know, house data, size of the house. Those things are kind of related. So not. So if there's anything that you can do, I think what they're talking about is separate features, separate outcomes.
And then they just interpolate with it. So, I guess the problem, so I don't understand what we generate, because I'm not a data scientist, so. If it's what she just described, it seems intuitively obvious that somebody would have. Or would you just,
I mean,
So unless we can
because
see
they
something.
can educate, if they can random educate, say someone at the spot.
Yeah.
Makes some ten. I mean, it also doesn't mean that with like real data to the side, you're going random accuracy outside of that. Something else. Some other people. But, yeah.
Well, I suppose if it was a combining, you could project it outward as well, instead of just interpolating between password.
Well, this is where I think if it was a case like that, maybe you would take a different approach, right? So sampling techniques might be useful in certain cases, but they're not always maybe the last resort, right? We talked about anomaly detection, we talked about cost weights, so you can approach this in different ways. Here, it's just, can we, if we are trying to generalize more and go with just producing more training data based off of what we already have, can we kind of create a data set that's a little bit better for training on problem? We can always evaluate it and go towards it. Okay, so
The important thing to remember, having been in academia, is someone got tenure because of it. That's the key part. No, but your concerns are well founded, and I think a lot of techniques that you see, they have really fancy names, but they are you going to hand me the microphone? I don't want to get too close to the mic. All right. I think a lot of these techniques, they sound somewhat fancy on the surface, but at their core, they should be intuitive. They should, when you break down the mathematics that sits behind them, the nicest techniques sort of make sense. I think when you look at it, if you look in their paper, they go into detail about core assumptions that they have behind the methods. And I think in a meetup, it's kind of hard to kind of choose, do we go deep into the assumptions and sit behind the methods or not? I think that's something that's sort of on.
thank you for okay. So the advantages here are that when we looked at oversampling from the minority class, we generated these very small decision boundaries. And now we're able to kind of generalize a little bit better, and we're able to create these less specific decision boundaries here.
I know this is just some sample that you threw up here, but to me,
this decision boundary doesn't seem any better than that one. In fact, would it be arbitrarily worse because it includes green ones?
Not necessarily, right? So if we were okay with the cost of misclassification, right? So we were okay with false positives, then this might actually be better and work better out of the sample.
On the rest of it.
Right?
Okay.
That's what we want, and it's not like we're gonna get something.
You're worried about just the sheer size of that being so tiny, it's gonna have a poor positive transaction.
Okay. So things to keep in mind. So when all the sampling techniques that we talked about here are always just being applied to the training set. So when you go about model evaluation, you have to make sure that you have not done anything to the testing set and that you're working with the natural data set as it is, right? A very realistic case. So in Python, you can look into stratified k-fold as a way of evaluating. And then in R, I resisted to put this up, but I did. Unbalanced, I don't know that package, but maybe you guys can mess around with that. In Python, there's Imbalanced learn. So that's one of the packages that I'm going to use for the example that we'll go through right now. And always read the documentation. Yay, documentation. So the demo that I'm going to do is on credit card fraud detection. So essentially, this data set has, much less than 1% of all transactions are fraud. So it's a very small positive class. And then what they've done to the data set is essentially full component analysis, where they basically, all the features are V1, V2, V20. You don't know what these features are. They're just, so that's how they'll appear in the data set when I pull it up right now. And then the feature class is the response variable, and it takes on a value of 1 and 0 other.
When we did the feature engineering credit card fraud, we would create, we have like maybe 6 features or 7 features. And we take those 6 or 7 features and we create up to 200 created feature engineering variables. And then we would use PTA and some of the other dimension reduction to get down to maybe 19 or 20 variables, and that would explain most of the variance.
Yep. So yeah, essentially that's what this happened here, right? So this feature set was probably hundreds of variables, hundreds of features, and they basically collapsed it down to I think it's a total of 30 variables, and those are the ones that we're going to do. Cool. Any questions? Awesome. And here I put up the pseudocode if you want to go through and read it yourself. Very interesting stuff. Cool. And then
So much learning.
There's no pop quiz.
I get it.
and then here are some really good resources that I like, especially I would recommend if you've never kind of dived deep into the ROC curve, this visual does a really good job of explaining the distributions and how that ROC curve is generated. And then this is where I got my data set from, and let's move to the demo. Cool. We good so far? Yeah? All right. Yeah, okay, cool. All right, so here is the notebook. So are we familiar with Jupyter notebooks? Okay, so this is essentially my Python notebook. Where do we begin? Do we need explanations of the libraries? I'll just do a brief walkthrough. So Pandas is going to be used for data manipulation. NumPy is for arrays, Matplotlib, and Seaborn will be used for the visuals that I make. And then I'll import a few others later with scikit-learn. So if you want to, side note, if you want access to my notebook and the presentation, it's all on my GitHub. And I can put that link on the meetup page if you want to walk through this. So the fraud data set I just pulled from Kaggle. Now the first thing that I would want to do is look at the shape, right? Wow, I've operated this whole time without my glasses. Okay, so the shape of this will give me the number of rows and the number of columns. right? So the number of rows, I'm dealing with 200,000 rows approximately and 31 features. Then I'll look at kind of the head of the data set to see what these features look like. So as expected, I have V1 through V28. I also have an amount and a time. And then the last variable here is class. And it's a binomial. And I'll see here that I'm just verifying that, yeah, in fact, I do have less than 1% of fraud in the data set. Just for fun, I'll plot some of the features just to see what I'm dealing with. So here I'm looking at the distributions of feature V2 and V3, and I see that they don't completely overlap, so they might be somewhat good in my model. The next thing I'm doing here, it's a lot of code, but it's essentially a few simple steps. So I'm taking the fraudulent samples and I'm separating them out from my non-fraud. Then what I'm doing is sampling 3%. The reason I did this is just so that when I run it here now, it goes quickly. Otherwise, you'd be here for a while. So I created a sample data set that has equal representation of fraud and not fraud as the original one. And then I created a testing set that's different from the sample set. Took it out, put them here, took it out again. And then we'll just run that. And so here in my sample set, I have about 8,000 samples, and I have approximately the same amount of fraudulent transactions, and the same with my testing set. So the next thing I'm going to do is I'm going to take out the class, take out the variable class and assign it to y, and then put all my other features in x. Are we okay here? Mouse. So y is going to have all of my, basically the classifications of fraud, not fraud, and everything in x will be my feature matrix. Then, since I want to visualize, so the point of this exercise would be to kind of gain an intuition of what's happening. So I can't visualize in more than 2 or 3, so I just chose 2, V1 and V3, and then I did the same thing for the testing set. Are we okay here? Okay, I'm okay to move slower or faster. Okay, so not a very intelligent classifier. We said this would do what? The classify everything as not fraud, right? So this might do a little better than that, but so I'm just choosing one of the available classifiers to me here in SVC. So we'll instantiate that. And so sklearn, for those of you guys who aren't familiar, sklearn is a machine learning library that is provided by Python. It's really great. It has access to a lot of different models, and it won't be what we use for the resampling. It'll be another library, but it's useful for the classification and regression models. So here we're going to fit to our sample data, right, x and y. And then I'm going to plot the decision boundaries. So this is just boilerplate code. I'm just going to run this and see what my decision boundary looks like for this case, right? So the purple is the majority class, and the yellow is the minority class. We're okay there? So the decision boundary is essentially saying everything here is has been classified as not fraud, and maybe the only 3 points that got classified as fraud are in those little circles. So not too intelligent, right? It wasn't able to kind of capture the samples over here at all. So so the things that we talked about, indirectly, I showed you guys a confusion matrix. It was that nice pie chart looking thing. So that was a confusion matrix. And so from sklearn, I'm just going to import a bunch of the metrics that we talked about. So the confusion matrix, precision, recall, accuracy, the ROC, all the good stuff. And we'll take a look at what it looks like. So what do we see? Oh, and what else will I do? I will show you guys this. So what's happened here?
8,000 samples in the 0,
We're correctly classified as 0.
So these are your predicted, and these are your actual, right? So this is actually negative, predicted negative, actually positive, predicted negative, actually positive, predicted positive. So what do we do here?
Predicted 1.
You got one right. But look, we have a precision of 1. But our recall is really bad, right? So remember, it's a trade-off, right? When we gain in precision, we lose in recall. We gain in recall, we lose in precision, right? So the way that we would have liked to make this a little bit better is maybe make more predictions, right? So we're okay maybe in this case, in the case of fraud, that we decrease our precision a little bit for the sake of correctly predicting more fraudulent cases, and maybe we just have more time to sift through the fraud. Now the accuracy, whoa, 99.8. Oh, good one.
What you're doing on top of
Yeah. Okay. But notice our accuracy looks pretty good, doesn't it? 99.8. If we take, here, let me see. If I take this and I'm just literally replicating exactly what I see the imbalance in the data set, right? So it's equivalent of just looking at how much of the minority class was prevalent in our data set, and that's approximately equal to the accuracy that we get here. So not that intelligent of a classifier. So we can also look at something called a classification report, which will basically print out for you the recall, the F1 score, and the support. You can look at that. And then the ROC curves. So here is the ROC curve that comes out of this type of model. So we see it does okay, but then eventually it does worse than random guessing. So maybe not the best, but we won't know until we do something else and compare it, right? So let's try something else. So we're going to resample using SMOTE. I'm going to try 2 different methods. I'm going to go with SMOTE, and then I'm going to do a random oversampler, so we can just do a comparison of what happens. So Imbalance Learn, check it out. It's a very, very good documentation there, so you can read about it. So I'm going to instantiate 2. I'm going to import them and instantiate them. And here I just want to point out the K neighbors is essentially saying how much oversampling do I want, right? So here, out of the 5 nearest neighbors, how many do I want to choose? And here I'm just choosing 1 or maybe 2. Maybe do 1. That's fine.
Where's the 5? Is it always 5?
It's always 5.
Okay.
Yep. So then I made a function called plot decision boundaries, and here I'm going to essentially fit to my sample data set on both, right? The oversampled and the SMOTE. And I'm going to plot their decision boundaries. So hopefully this will be a nice visualization. Hitting SVM, here we go. So here's the first case. So the first case that we did here was, what did I do here? Random oversampler. So what this has done, notice I've set my alpha value, which means the transparency of the points. So I can see exactly what's going on here. So I see that here there's a dense majority class, but I can also see that these minority classes were just oversampled over and over and over again. So it's very clear what's happening here, right? So the very dark just means that those points are occurring over and over again, which is why these decision boundaries are looking the way they do. Versus if we did a resampling, then notice now we have a little bit more of a generalized, and notice that this doesn't change, right? This is what I'm training on, And this is the decision boundary that results on my regular data set. So here I've generated a little bit more data points there, and I've generated data points around here, so I have a more generalized decision boundary. Are we okay? So now I'm going to run my confusion matrix, and I see that, yay, I've classified 7 times more, and I brought my recall up to 50%, which is decent. My precision, obviously, I'm paying, but I'd rather classify and have a lot of false positives in this case, and I'm okay with that, as long as I can classify more of the actual fraudulent cases. And notice I'm always looking at the testing set, right? So it's the non-balanced version. And I can take a look at my classification report and the ROC. And I see that I've achieved a much nicer ROC curve and an area under the curve of 86, which is better than the 70-something that I had up there. So I think I'm happy. And that's all I have. Any questions?
Why could run this with only one paper?
I could. That just means I'm 100% creating 100% more data points.
What if you inflate it to like 5?
Yeah, I can change it. I do 2. For 3? We went for 2. 7. Blow it up. Okay. So what it'll essentially do is just create more data points, right?
Are you expecting drastically different results by changing that in this case?
It depends on the features you're working with, right?
I guess in this case, we don't really know anything about the features.
Yeah, exactly. I just blindly chose them, and I'm happy for you guys to take this one step further, right? So take this notebook, play with the different features, see what happens, and change the parameters in the code, and see what happens. I think this is the best way to start understanding what it's doing, right? So in any normal case, you're not going to be able to just visualize all this stuff, right? You're going to have to just rely on the AUC and ROCs and stuff like that. So having it in 2 dimensions is really just for building an intuition.
You should really A/B test this and have 2 models, one different, one was say random oversampling, one was SMOTE, and then see how your business decisions follow from that. How would you gain validity that your SMOTE was doing a better job or a worse job?
Well, so it's through this, right? So I've plotted my ROC curve to see that it actually performed better than what I had prior, but I can create an ROC curve for a bunch of different models, right? I can try a bunch of different techniques and see which one is performing best.
Did an analysis in one of our classes, and we found that when we use certain variables, we had a higher AUC curve, on the plot or ROC map, but the variables were not in the control of the company, the client company. And so we opted in our presentation to pull some of the variables out that explain the variance and had a lower score, but all of those variables were within the control of the client. It was much more intuitive for understanding.
All right, anything else?
Is there any characteristics of that data set that you could look at and say that you can be more or less amenable to SMOTE? Like, the shape of the distribution of the minority set? Like, say, well, these ones all tend to fall in a linear line, so they sample synthesize what we tend to be in that line too, versus something that's more multi-dimensional. Because obviously there's only 2 variables right here, but there could be a n. It's going to be an n-dimensional space, right? So it's.
Well, that's what I was going to say, is that most of the time you're going to be dealing with so many features that you won't know, right? So
you won't be able to visualize it.
No.
In this case, you had like 28 features or some parts. I'm thinking about if we flip this back, so we will games, so great. So I'm thinking if we flip this back over, we wanted to determine which of these, now that we sort of built the model, we think we can get. Is there ways to now take the 28 and say which of these do we think are actually significantly contributing to this decision? So can you do that from where you are now?
that would be a different type of analysis, right? So if you're just saying which ones are playing a role in the decision or not, yeah. So we could probably approach this from the standpoint of feature selection and just look at, basically you can run like a random forest or other algorithms that will basically tell you the importance of that feature to that decision, right? So to that class, how much is it contributing to the model, and you can basically rank order them and figure out, okay, the top 5 or something like that. In this case, they've altered the dimension of the feature space is now not in terms that we understand anymore, right? V1 doesn't mean anything. In our case, if we care about interpretability, we won't do any type of dimensionality redemption or anything. Cool. All right. Well, thank you guys so much for coming. I had a great time, but this doesn't end until 9, so feel free to mingle and hang out. And I don't know if we can play music. Yeah.
So we're gonna do our best to hold this about once a month. The next, I believe, probably 1 or 2 sessions will focus on time series work. So things that are, and time series has a lot of stuff to it. We'll try to make sure the focus remains on how does this end up affecting the business? How does, because we've all been in meetings where people say, hey, I see the line going up, right? That's not what you want, right? So time series is a really fascinating idea, and it's very different than fitting lines to data, which is what we think about when we're doing models. So we'll be digging into that, and look forward to having you guys here next time.
Yeah, I think I'll try a cadence of once a month. Wednesday happens to be the day I chose for this month, but we'll probably do it to Tuesday or Thursday, and we'll try to keep it consistent. And I'm more than happy if any of you guys have interesting things that you're working on that you'd like to discuss and talk about. Talk about it. So chat with us. All right. Have a good evening. Thank you.